Jai Hind students, being a good student is less about the ability to rot and more about the desire to learn. So students, I always keep saying, have that burning desire to acquire knowledge and don't cram anything, don't rot anything, avoid rot learning. Do try to understand the concepts. That will make the studies very simple. You will start taking interest in your studies. So with that students, let's begin this session. Welcome to my YouTube channel. We were discussing applications of Biot Savart law. We have discussed the first application of Biot Savart law, that is the strength or the magnitude of the magnetic field at a point due to a straight current carrying conductor. The second application is we will make use of Biot Savart law to determine the expression for the magnetic field at the center of a current carrying loop. So before we start with the second application, let us recall Biot Savart law. Biot Savart law gives the strength of the magnetic field, right? And in the case of Biot Savart law, the strength of magnetic field at a point due to a small elementary portion, it's given by mu naught divided by 4 pi I dl sine theta divided by r square. Now this is the small elementary portion dl. I dl stands for the current element. You are aware magnetic field is due to a current element. This is the observation point and this is theta students. Theta is the angle which the direction of the flow of current or the current element makes with the line joining the center of the elementary portion to the observation point. And r is the distance between point P and O. Right students? So let's begin. Here our objective is to determine the strength of the electric field at the center of a current carrying loop. Right? So suppose this is the current carrying loop under consideration. Suppose current is flowing in the clockwise direction. This is the direction of flow of current. And this loop consists of a single turn and let O be the center where the magnetic field due to this current carrying loop is to be determined. And also suppose R be the radius of the loop under consideration. Let's consider a small elementary portion. This small elementary portion is considered to be PQ. This is P and this is Q. Now as you are aware, this elementary portion when measured along the direction of flow of current, then ideal, it represents a vector quantity known as current element, isn't it? So current is flowing along this direction. So at this point it will be given by drawing a tangent. So the direction of the current element would be like this. This is the direction of current element. Right? And this is the center of the observation point and this is the line joining the center of the observation point or the center of the elementary portion to the observation point. So this is r cap. It will be directed along this direction. So students, what's the angle between these two? It is 90 degree. In case of an arc, in case of a circular portion of a conductor, what happens is the angle theta, which is the angle which the direction of the flow of current makes with the line joining the center of the elementary portion to the observation point, is always 90 degree. So here theta is 90 degree. So what you get is magnetic field at the center due to the small elementary portion. As per Biot Savart law, it will be given by mu naught I dl sine 90 divided by 4 pi r square. R is the distance between the center of the elementary portion and the observation point, which in this case is the center of the loop, right? Theta over here is 90 degree. Sine 90 students, we are aware it's equal to 1. So what you get is dV, it's equal to mu naught I dl divided by 4 pi r square. Students, in the case of circular loop, this r radius, that will remain constant. So the only variable is dl, so we can directly integrate it. So net magnetic field at the center of the circular loop is given by this symbol indicates that the magnetic field is to be determined at the center of the circular current carrying loop, right? It is given by mu naught I divided by 4 pi r square integration of dl. Right, students? Rest all the terms are constant, so it has been taken outside the integration. Now integration of dl. This is small elementary portion dl. This one is small elementary portion dl. If we combine these small elementary portions, that will give us the entire length of the current carrying loop, and that will be obviously equal to 2 pi r, isn't it? So what we get is mu naught I divided by 4 pi r square multiplied by 2 pi r. So the magnetic field at the center of a current carrying loop is given by mu naught I divided by 2r. This is the formula for the magnetic field at the center of a current carrying loop, right? This gives the magnitude. Now what about the direction, students? Current is flowing in the clockwise direction. So look, at this point, the magnetic field lines will enter like this. It will enter like this. If you apply right hand thumb rule, the magnetic field lines will enter this face of the loop. So it will be perpendicular to the plane of the loop and in the inward direction. And this is the symbol which we make use of to indicate the direction of the magnetic field perpendicular to the plane of the loop and directed inwards. Right, students? So this is the formula. Now let's discuss some special cases. Right? Case 1. Let's discuss some special cases and let us consider case 1. Case 1 is, students, if this loop contains n identical turns, if it contains n identical turns, then what will happen is, due to a single turn, the magnetic field is directed inwards. Due to the second turn, it will be again directed inwards. Due to the third turn, it will again directed inwards. And magnetic field being vector quantity, and due to all the turns, the magnetic field is directed in the same direction. So it will get vectorially added up. So net magnetic field at the center, when it contains n identical loops, would be B plus B plus B plus B n times. So it will be equal to n times the magnetic field due to a single turn. So in this case, the net magnetic field would be given by n times the magnetic field at the center due to a single turn of the loop. Right? So that is mu naught I divided by 2r. R is the radius of the loop under consideration. Right? Case 2. In case of a semicircular loop, in case of a semicircular current carrying loop. So diagram would be somewhat like this, This is a semicircular loop. Suppose current is flowing in the clockwise direction, and this is the center. Due to the circular loop, the magnetic field at the center is mu naught I by 2r. Therefore, due to the semicircular loop, the magnetic field will become half. So in this case, the magnetic field at the center of a semicircular loop would be given by mu naught I divided by 4r, which is equal to half the magnetic field at the center due to a circular loop. Again, you can easily verify the statement. If you consider a small elementary portion over here, the current element will be directed along this direction, ideal. This is the center of the elementary portion, and this is r cap. The angle between these two is 90 degrees. So we should get the same expression. Here on integration of dl, we will get the length of the semicircular loop, which is equal to pi r. So integration of dl, instead of 2 pi r, we will get here pi r. So after solving, we will get mu naught I over 4r. So students, this is the formula for the magnetic field at the center due to a semicircular current carrying loop. There is still another special case left, right? So that is the magnetic field at our center due to a current carrying arc. subtending an angle theta at the center. So let's find out the expression for that. So we'll consider arc. Okay, case 3. Magnetic field at the center due to a current carrying arc subtending an angle theta at the center. So this is the situation basically. This is the diagram, this is the center, and this is suppose an arc, right? Say current is flowing in the clockwise direction, and this arc is of radius r, and it is subtending an angle theta at the center. Theta is the angle subtended by this current carrying arc at the center. So we need to find out the magnetic field at this point. Suppose the length of this arc is L. So we are aware the magnetic field is given by mu naught I over 4 pi r square integration of dl, right? Here integration of dl will give you the total length of the arc. In the case of a circular loop, integration of dl will give us 2 pi r. In the case of a semicircular loop, integration of dl will give us pi r. In the case of an arc, integration of dl will give you the length of the arc, which is L. So what do you get in this case? So magnetic field due to a current carrying arc would be given by mu naught I divided by 4 pi r square. Integration of dl, that will give us the total length of the arc. It is L. So in terms of theta, how to write it? Angle subtended theta, it will be equal to length of the arc divided by radius. So L can be written as theta multiplied by r. So it can be written as mu naught I divided by 4 pi r square. In place of L, write theta into r. This r get cancelled. So we are left with magnetic field at the center due to current carrying arc is given by mu naught I theta divided by 4 pi r. This is the magnitude of the magnetic field at point 2 due to this current carrying arc subtending an angle theta at its center, right? And direction, students, we are aware, we can make use of right hand thumb rule. Suppose here, what will be the direction of magnetic field? Current is flowing along this direction. So let's make use of right hand thumb rule. Thumb indicates the direction of flow of current. So the direction in which the rest of the fingers curl, that gives the direction of the magnetic field. So at point 2, the magnetic field lines will enter. So the direction of magnetic field at point 2 would be perpendicular to the plane and directed inwards. And the symbol which we use to represent the inward magnetic field is like this. So this represents the direction of the magnetic field. So students, I hope you have understood this topic. So we have derived 3-4 very important formulas, right? And as I have told you numerous times, once the theoretical portion is over, once the derivation part is over, you are supposed to remember each and every formula, so that while solving numericals, we can directly make use of these formulas, right? There shouldn't be any sort of ambiguity. Clear, students? So, before starting with some interesting numericals, let us recall all the formulas that we have discussed so far. So basically, we have started with a straight conductor, isn't it? So there are several formulas which we have discussed till now, or rather we have mathematically verified. Okay, let's discuss those formulas once again, right? First, magnetic field due to a straight conductor, having endpoints A and B, subtending angle phi 1 and phi 2 with the reference line. What is the formula? Mu naught I divided by 4 pi A sin phi 1 plus sin phi 2. This is the first formula, right? Second, the magnetic field at a point due to a straight current carrying conductors whose both ends extends to infinity, like this. Both the ends extends to infinity. So here the formula would be Phi1 is 90, Phi2 is 90, sin 90 plus sin 90, 1 plus 1, it will become 2. So you'll get mu naught I divided by 2 pi a. So this is the formula for the magnetic field at a point due to a straight, infinitely long current carrying conductor whose both the ends extends to infinity. Third, magnetic field again due to a infinite straight conductor, but in this case one end is fixed and the other end extends to infinity, and the observation point is just in front of the fixed end of the straight conductor. So in this case the formula is mu naught I divided by 4 pi. Here phi1 would be, one of the angle would be 90 and the other one would be 0. So sin 90 is 1, sin 0 is 0. So 1 plus 0 1, so we will be left with mu naught I divided by 4 pi. Right? Fourth, magnetic field at the center of a circular current carrying loop. It is given by mu naught I divided by 2r. R is the radius of the loop under consideration, right? For n turns like this, for n identical turns, what is the formula? N times the magnetic field at the center due to the current carrying loop. It will become n times. Okay. Sixth, the magnetic field due to a current carrying semicircular loop at its center, it will be equal to half of this. So what do we get? Mu naught I divided by half of this, we will get mu naught I divided by 4r. Clear, students? Seventh, magnetic field at the center of a current carrying arc subtending an angle theta at the center. So what is the formula? Just now we have derived. It is mu naught I divided by 4 pi r multiplied by theta. This is the formula. Mu naught I theta divided by 4 pi r. Theta is in radians. Clear, students? So these are some very, very important formulas. And one more thing, student. The magnetic field at any point on the axis due to a current carrying conductor is always 0. Like this is a straight current carrying conductor, right? It bends like this. So this is the first portion, this is the second portion of the same conductor. Now look, this point A lies on the axis of first conductor. So magnetic field at point A due to the first conductor would be always equal to 0. What is the reason? The magnetic field at any point on the axis of a current carrying conductor is always 0. This also we have discussed. So that's again a very, very important result. So magnetic field at any point on the axis of a straight conductor is always 0. Clear, students? So I hope you will be able to remember all these formulas. So before we start with the numericals, please students, you need to remember all these formulas along with the derivation. Clear? Okay. Let's start with a simple question now. Let's practice some numericals based on the applications of Biot Savart law. Okay. First question is, suppose there is a square loop each of side A and current I is flowing in that loop. We are supposed to find out the strength of the magnetic field at the center of the square loop, right? So this is the question. This is a loop. It's a closed loop and current is flowing along this direction in the clockwise direction, and the side of the square is A. We are supposed to find out the magnetic field at the center of the square. Now students, center of the square means it must be the intersection of the diagonals of the square. So this must be the center. It is the intersection of the diagonals like this. Clear, students? So it has got 4 identical sides. isn't it? Each of length A, each carrying current I. So what we do is, here we will try to find out the magnetic field at point O due to one side of the square. And then we can generalize the result for 4 sides, right? So this is suppose first side, this is second, this is third, and this is fourth, right? Let's consider this straight conductor. This is the straight conductor. Due to the straight conductor, the magnetic field at point O would be directed inwards. Due to the second one, the magnetic field will be always directed inwards. Third one, again, make use of right hand rule, and you will get that the magnetic field due to each of these 4 portions at point O will be directed inwards. So the direction of magnetic field due to these 4 segments is same. So they will get added up. And also the length of the current carrying conductor, the magnitude of the current flowing through each part, as well as the distance, perpendicular distance of the observation point from this current carrying conductor, that is also in all the 4 cases same. So magnitude would also be same of the magnetic field at point O due to each of these 4 segments. So what we do is, we will try to find out the magnetic field at point O due to any one part or any one side, and then we will multiply it by 4. So that will give us the total magnetic field at the center of the current carrying square, right? So what about the net magnetic field then? It will be equal to 4 times the magnetic field at point O due to any one side of the current carrying square. Clear, students? And what will be the direction? Direction would be inwards, like this. The magnetic field at point O due to each of these 4 sides, current carrying sides, would be directed inwards. So that is the reason why the net resultant magnetic field gets added up. B plus B plus B plus B. So it will become 4 times the magnetic field. And direction would be inwards. So direction that we have already determined. The direction of the magnetic field at point O, in case the current flows in the clockwise direction, would be perpendicular to the plane of the square loop and will be directed inwards. Right? So now let's get the expression. Now due to a straight conductor whose both the ends are fixed, the formula for the magnetic field is given by mu naught I divided by 4 pi perpendicular distance of the observation point from the straight current carrying current. This is the perpendicular distance. So it is R. It is considered to be R. And then sine phi 1 plus sine phi 2. This is the reference line, and these are the 2 end points. So these 2 end points of the straight conductor with the reference line makes an angle of phi 1, phi 2 over here, each being 45 degrees. Am I clear, students? Diagonals of a square bisect at right angle. So phi 1 is 45 degree, phi 2 is 45 degree. So here we get sine 45 degree plus sine 45 degree. So we can easily solve it. So 4 times mu naught I divided by 4 pi. R needs to be expressed in terms of A. R naturally would be equal to A by 2. So it is A by 2. Sine 45 plus sine 45, that will give us 2 sine 45 degree. So 4 get cancelled. So what we get is 4 mu naught I divided by pi A. Sine 45 degree is 1 by root 2. So on rationalizing, what we get is multiply and divided by root 2. So what we get is 2 root 2 into root 2 will give us 2. 4 divided by 2 will be left with 2. So 2 root 2 mu naught I divided by pi. So this is the expression for the net magnetic field at the center of a current carrying square loop. And in case the current in the square loop flows in the clockwise direction, then the direction of the magnetic field, as discussed earlier, is perpendicular to the plane of the loop and directed inwards. This is the symbol for the direction of the magnetic field, which is perpendicular to the plane and directed inwards. So this is the complete result. And always while solving numericals, in case you need to find out a vector quantity. So please students, express its magnitude as well as direction. So this will be the complete answer. This is the magnitude and this is the direction. I hope you have understood the concept, how to proceed with such questions, isn't it? Let's try another one. Instead of considering this square loop, we can consider a triangular loop, right? So let's try that. So second question which we are trying to attempt is a question which is similar to the previous one, just now we have done. Simply, a square loop will be replaced by a triangular loop. Let us consider a triangular loop whose all the three sides are same, say A. And suppose current is flowing in the anti-clockwise direction like this. All the sides are equal. Our objective is to determine the magnetic field at the center of the triangular loop. Now students, center of a triangle is the centroid, which is the intersection of the medians. So let me draw the three medians. These are the medians. Right, these are the medians. So this is the centroid. Let us represent it by G. Now we are aware centroid, it divides the median in the ratio of 2:1. We are aware of it, isn't it? So A is the side and current I is flowing along this direction. So again, the approach with which this question is to be done is similar to what we have done in the previous question. Look student, all the three sides are of equal dimensions. In each of these three sides, same current is flowing. The distance of the observation point, which is point G over here, from the straight current carrying conductor is same. This is the perpendicular distance, this one. Let us consider it to be R. This is the perpendicular distance. This is the observation point and this is the perpendicular distance of point G, which is the observation point from each of these three sides. Right? So as a result, we can safely predict that the magnitude of the magnetic field at the center due to all these three segments is equal and also in the same direction. Now what will be the direction? Due to this part, current carrying part, the magnetic field at point G would be like this. The magnetic field lines will come out of point G. Due to this part, again applying right hand rule, we get that again due to this part, the magnetic field lines will appear to come out of the plane. Due to this part, again the magnetic field lines will appear to come out of the plane. So the strength of the magnetic field as well as the direction at point G due to these three parts are same. Therefore, magnetic field being a vector quantity will add it vectorially. And when the vectors are having same direction, then they will get added up. So students, net magnetic field, it will be equal to B plus B plus B. So it will be equal to thrice times the magnetic field at point G due to one side, current carrying side. So students, the net magnetic field would be given by thrice B, right? So 3 times the magnetic field at point G due to one side, one current carrying side of the triangular loop, right? So that as per Biot Savart law is given by mu naught I divided by 4 pi perpendicular distance. The perpendicular distance of the observation point from the straight current carrying conductor is R. So it will be R. Sin phi 1 plus sin phi 2. This is sin phi 1. This is the reference line and these two are the end points. So each angle is 60 degrees. As we are aware, each part it will be subtending an angle of 120 degrees. So this being angle bisector as well as the median, each angle which the end points makes with the reference line would be 60 degrees, isn't it? So it will be sin phi plus sin phi 2. So sin 60 plus sin 60. So let's solve the equation. Thrice mu naught I divided by 4 pi r. Sin 60 plus sin 60 will give us 2 sin 60 degree. Now students, look, in the question it is given the triangular loop is of side A. So our objective is to convert this r in terms of A. Now students, we are aware of the height of an equilateral triangle, right? This is the height, and height of an equilateral triangle is root 3 by 2 into side. Over here, side of the equal triangle is A. And as I've told you, this centroid, it divides the median in the ratio of 2:1. So this part is 2 by 3rd of the height of the equal triangle, and this part would be 1/3 of the height of the equal triangle. So R, it is equal to 1 by 3 times the height of the equilateral triangle. So substituting the value of h over here, what we get is root 3 by 2a. So this is the expression for R in terms of A. You can get the same result alternatively as well by using trigonometry. It's a right angle triangle. So considering the trigonometric function, you can easily get the value of this. This is A by 2. So by getting the relationship in perpendicular base, maybe you can make use of tan 60 degree. Then also you will achieve the same result. Clear, students? Now let's substitute this value of R over here and let us get the result. So what you get is net magnetic field at point G due to this current carrying triangular loop would be given by thrice mu naught I divided by 4 pi in place of R, right, root 3a 6 twice sine 60. Sine 60 is root 3 by 2. So it will be root 3 by 2. So let's solve it. Root 3 get cancelled. So 2 get cancelled. So here we will be getting 3 2 6 2. So it will be equal to 9 by 2 mu naught I divided by pi a. So students, this is the magnitude of the magnetic field at point G. So this is one part of the answer. And second part is the direction. As I told you, magnetic field being vector quantity, its magnitude as well as direction needs to be written, right? Regarding direction, we have already found the direction of the magnetic field over here would be perpendicular to the plane of the loop and directed outwards. You can check it. The current is flowing in the anti-clockwise direction. So make use of right hand thumb rule. So you will observe that the fingers curve in the outward direction from point G. So the magnetic field lines from point G will appear to be coming outwards due to each of these three parts of the triangular loop. Right? So net magnetic field direction is perpendicular to the plane of the triangular loop and directed outwards. So students, I hope you have understood this numerical. Do practice as much numericals as possible. Right? So I would like you to join in my next lecture. Till then, do take very good care of yourself. We will discuss some other very interesting numerical problems based on Biot Savart law and its application. So till then, goodbye and do take very good care. Thank you.